In this project, we incorporate machine learning into the histopathology decision-making process to assist the histopathologist for more efficient and accurate decision-making. Initially, a consultant will prescribe a biopsy to diagnose whether there are any cancer threats. Then, a surgeon will take a tissue sample from the suspected area. After retrieving the tissue sample, it will undergo a process called staining and will be scanned using a digital scanner. This scanned digital image of the tissue is called a whole slide image. In this project, we address 5 major challenges. Usually these whole slide images are very large in both size and resolution and inefficient to use in machine learning algorithms. Therefore, we process the whole slide images in patch level. Due to the large resolution of whole slide images, it is extremely costly to get pixel level annotations. To overcome this issue, we follow a self-supervised learning approach. There are different clinical tasks available such as patch level classification and slide level classification. We propose a task-agnostic model that can address all these tasks without any architectural modifications. And our proposed model is dataset agnostic as well, which can be used on different data types. The main concern of a machine learning algorithm is the lack of interpretability. In order to address this issue, we provide an uncertainty score with each prediction informing the histopathologist how confident the model is in its prediction. In addition to that, we provide attention maps which further enhance the interpretability. We use the patch chameleon dataset for patch level classification benchmarking. It consists of images with 2 classes taken from lymph node section of breast cancer patients. NCT-CRC 100K dataset has images with 9 classes taken from colorectal cancer patients. This dataset is used to benchmark patch-level multi-class classification. To benchmark whole slide classification, we use Chameleon 16 dataset. It has 400 lymph node whole slide images taken from breast cancer patients. We use SimCLR v2 as our base model. SimCLR v2 consists of 3 main training steps. Initially, a model will be pre-trained on large unlabeled dataset using contrastive learning. Afterwards, the encoder is fine-tuned on a small fraction of labeled data followed by a knowledge distillation step. We introduce an uncertainty loss to quantify model's confidence on its own predictions. Then, we propose a novel training method in the fine-tuning step to incorporate the quantified uncertainty to its own training process. We term this as uncertainty-aware training. In this process, we iteratively add 1% of data with highest uncertainty to the labeled dataset until we reach 10% of the whole available data. We empirically show that our proposed uncertainty-informed training method achieves the state-of-the-art result on both binary and multi-class patch-level classification. At the inference, our proposed uncertainty-aware SimCLR v2 provides an uncertainty score along with its prediction. This confidence score will help the doctors to decide whether further human inspection is needed in each scenario. We have used TSNE techniques to visualize feature space of our encoder on NCT-CRC 100K dataset. There are 9 classes in the dataset and you can see 9 well-separated clusters in the TSNE projection. Each dot represents an image patch. We have added the patch image, its prediction, and the uncertainty score to the projection for easy inspection.
We perform whole slide image classification using a multiple instance learning framework. Here we present the training settings of a multiple instance learning framework. Given a whole slide image as the input, it is first splitted into patches. These patches are then randomly divided into multiple pseudo bags. Patches from each of these pseudo bags is then forwarded to an encoder. For this encoder, we use an encoder pre-trained using our Sinclair v2 framework. The patch level features learned by this encoder is then forwarded to a Tier 1 model which learns a bag representation. These bag representations are then aggregated using an attention mechanism at the Tier 2 model to generate a slide level representation. It is then used to find the class label for the slide. During inference, we forward this whole slide image through the architecture, and as an interpretable output, we generate it at an attention map.